Okay, so here we are. We were talking about parametrized curves last time, but just barely. I reminded you that there existed this thing called a parametric curve, and keep in mind that gives position in Rn as a function of time, which is the input variable, domain being just R or some subset of R. Okay, so let's think about what would a derivative matrix for this kind of a function look like. Well, I mean, you can just write it down, right? We've got output variables, we've got input variables, we've got a rule for how to construct a derivative matrix. The weird thing is we only have the one input variable, so we only get the one column for the derivative matrix. And that's where you put all those partial derivatives. Oh, wait, they're not partial derivatives. They're all derivatives with respect to, in fact, just a single variable. There are no other variables to hold constant. So these are literally single variable derivatives, D, not partial. Okay, is everybody with me? All right. Okay. All right. So, so we get this. And then you look at that expression, and my gosh, if they're single variable derivatives, isn't this just exactly the same as if we were to literally take the single variable derivative of a parametric curve? Now, we haven't talked about that before, but if you look at this expression, not a derivative matrix. This expression on the right is just the Math219 single variable, definition of a single variable derivative. And notice you have to subtract now vectors, because this is a vector valued function, but that's no problem. You can totally subtract vectors. You have to divide by h. Cool, it's a scalar, no problem. You can totally write that down. There's really nothing about the classical single variable definition of a derivative that you can't do in this case. So we have, you might say, a vector dx dt representing the classical single variable derivative. So that being the case, now just notice these two things are the same. Right? This derivative matrix is the same as the single variable derivative that we recall from long ago. Okay, so that's kind of nice. What does it look like? Now you might be thinking, aha, I remember this, rise over the run, must be a slope or something, right? But it's not. How could this be? This is a single variable derivative, and single variable calculus classes derivative equals slope. Why not here? The answer is, in single variable calculus, they kind of gloss over the fact that, it's only a slope if you're looking at a graph. They gloss over that because they're always looking at graphs. They're basically never looking at anything but graphs. Minor exceptions here and there. This is not a slope because we're not looking at a graph. We are looking at pictures like this, where we have a curve that's going through the target. There's no t-axis on this picture, right? T is not represented at all. T is not in the target. And we are not looking at this, smash together all the variables, Frankenspace, I like to call it, because you have input variables and output variables, and you kind of smash them together to create a new thing. Not at all. So we have a totally different geometric interpretation question. What you'll notice pretty quickly is not such a deep pull here, but this numerator just represents displacement, right? Between time t and time t plus h, those are two positions. The difference of two positions is a displacement. What is h? H is the amount of time between t and t plus h, right? So this is literally displacement per unit time, which is velocity. That's the physical definition of velocity. Right? So this is a different geometric interpretation. The derivative represents, I hope I can do this, represents a tangent vector to the curve, for one thing. but also a vector whose magnitude represents how fast is this parameterization tracing out that curve. So literally just a velocity vector. So y'all may recall this result from Calc 1 classes. Sometimes you interpret derivative as velocity, right? In fact, when they do that, when they give you, some story about a car driving along a road and, the amount of, which mileage marker you are on the road at a function of time, that kind of thing, and they want you to compute the speed, right, of the car. Yeah, well, derivative gives you the velocity, right? Kind of goes under the radar, but when you have that scenario, notice that they don't draw the graph of position as a function of time, right? Very important. Okay. All right, is everybody on board? Any questions? Likewise, by the way, second derivative is acceleration, also a familiar physics idea, perhaps. Okay, so a couple of examples just to get some algebra going. By the way, I'm remembering now I have this button up here that I can press that gives me a little bit more screen. I don't know why I can't remember to do that. Feel free to remind me, by the way, if you want to see more screen at any given point in time. So, yeah, and maybe I'll zoom in too. There we go, that's nice. Okay, so here's an example of how to make use of these ideas. Suppose we have some particle that's moving around through space, and notice you're not given position as a function of time. You're given velocity as a function of time. And a starting point, at t equals 0, we're at 5, 6. Given this, two questions: what is the acceleration and what is the position? So the acceleration is a pretty easy question. Acceleration is literally just the derivative of the velocity. All right, so you take the derivative of that given velocity. Boom, we're done with the acceleration. Everybody happy? All right, so what about position, though? Okay, well, here's the thing. If velocity is the derivative of position, kind of think about the grammar of it all, that means that position is the antiderivative of velocity. Make sense to everybody? Y'all have probably seen a single variable version of questions like this, right? Pretty common story. Very minor note that I don't want to spend too much time on, but a lot of people will call this the integral of velocity, and yeah, you can make a case. But what I have written down here is specifically an antiderivative. I make the distinction. I think the distinction is important. An antiderivative of a function is another function. An integral of a function requires designating an interval over which you're computing that integral, and the value is a number, not a function. Right? So we have these two distinct concepts. There's the concept of an integral, aka Riemann sums and all that, right? Area under a curve, if you like. And then there's this concept of an antiderivative. Now they're very closely related, right? Fundamental theorem of calculus, blah, blah, blah. But nevertheless, just because they're closely related does not mean they're the same thing. And this is another one of my sort of pet peeve soapbox topics that I could spend far too much time on in class. But I just want to warn y'all, please do try to be aware of that distinction. It is important to when you have two similar but distinct ideas, it's valuable to have different words to describe these two similar but distinct things, because sometimes you might need to distinguish them. So it's always bugged me. The term indefinite integral, right, was created to allow for this confusion to perpetuate, right? It's the most ridiculous term I've ever heard. I very much dislike the term indefinite integral. Why not just say antiderivative, right? That's more directly saying exactly what that is. Okay, I'm going to get off my soapbox. By the way, if you're not clear that you are following all the stuff that I was saying here, I made a 30-minute recording of me sort of venting about all of my frustrations about high school mispresentations of integrals, and it's on my YouTube channel, Miscellaneous Topics playlist. It's called What is an Integral? And you can hear me gripe for half an hour on this subject, and that might help if some of this might seem a little weird. Okay, moving along. So let's actually do this one now here. Antiderivative of velocity. No problem. The velocity was given. Here it is. Right? Velocity right there. Take that antiderivative one component at a time, as one might expect. Right? Easy integrals, you can do that, of course. Don't forget, of course, though, that when you do... Look, I just did it, didn't I? I said integral. I meant antiderivative. I didn't get brought up right. When you do an antiderivative, don't forget your plus c. Right? So you have a plus c in each coordinate, which means altogether you have a plus c vector. And just like in single variable calculus, you have to evaluate that integration. Again, they call it an integration constant. I've never heard anyone say anti-differentiation constant. So anyway. We do that by plugging in t equals 0. So I'm going to take t equals 0. I'm going to plug that in to this equation. And plugging in t equals 0. If I can hit the thing. There we go. T equals 0. Goes into there and into there. And, well, the position at t equals 0 is given, right? And I can evaluate the algebra here, and the c comes along for the ride. And so my equation, that blue equation, when you plug in t equals 0, whoops, just turns into this. Everybody happy? Easy to solve for c. Once you know c, you put it right there, and then you're done. Okay, now I want to address a common mistake that students make. Extremely common. A lot of students very regularly will just say, "Oh yeah, the c. Oh yeah, that's always the initial value," and just go with that from there. I need a little bit more screen here, don't I? There we go. Just plug in the initial value. That's always the answer. No, it isn't. Pretty clearly not, right, in this case. So don't make that mistake. This is ridiculous. And there's two things that are bad about this. I want to make sure we're very clear on what the two things are. One is that it gets the wrong answer, and I'm pretty sure you believe that matters, right? But there's something else that I think is even worse, is that it's invalid reasoning, right? This doesn't get a wrong answer because of like an arithmetic mistake. There's all sorts of innocent ways of getting wrong answers that are nowhere near as bad as completely non sequitur, non-mathematical reasoning, right? It just doesn't make any sense, right? So keeping in mind on exams, the way exams are graded, right? You're not graded by whether you have the answer at the bottom. The answer is next to irrelevant, right? What you're graded on is what can I confidently conclude from what is written about your reasoning. Your proficiency with the ideas that are necessary to doing the reasoning to solve the problem, right? This is completely invalid reasoning, and so that's a big deal. Make sense to everybody? You can trace it back, by the way. Where did this myth come from, right? If there's hordes of students out there claiming the integration concept is always the initial condition, why would they think that? And they think that because in a lot of high school math classes, it always works out that way. How could it be that it always works out that way? And the answer is because in a lot of high school classes, this is always all zeros. Because when you plug in t equals 0 into this, you get all zeros. Why would you get all zeros when you plug into this? It's because they give velocity vectors that are polynomials. And if you have a polynomial, the antiderivatives always, every term that you write down has a factor of t in it, and then you plug in t equals 0 and it all disappears, becomes all zeros. Right? So that's where the mythology comes from, but it remains that it's still just not true. Right? That's a broad statement. So heads up. Okay. All right. Yeah, I've already kind of given this speech here, vector valued antiderivatives. Please don't conflate this with being an integral. Some students will look at this right here and think, okay, so I guess we're looking at the area under the velocity curve or something like that. And it's just absolutely not what this is. In multiple ways, not what this is. So we'll talk later about integrals and what integrals mean in a multivariable context and how to make sense out of it. Okay. All right. Quick reference. There's notes on the content syllabus that we're skipping all of the, what I'm going to loosely call here, the Kepler stuff. Interesting, historically significant calculations, but it's kind of a digression, and we're in a massive rush, and it's not part of the prerequisite trail for any other material that we're going to cover. So you're not responsible for it. Take a look if you're interested, curious, looking for a little mathematical entertainment or something, but you don't have to. It's not fair game. That said, you are responsible for these two formulas here in Proposition 1.4, which is in those pages, right? I'm picking out this in particular as stuff I do want you to know. It's just kind of, you might say, a couple of product rules for when you're doing dots and crosses of vector valued functions. That's kind of exactly what you would expect or hope, perhaps. And we're going to make use of them here and there, so make sure to remember those. Okay, moving on. Back into section 2.5. So we're going to talk about the chain rule now. I'm sure y'all remember the chain rule. There's different ways to think about the chain rule. You can think of the chain rule as a statement about derivatives of compositions of functions, which is fine. There are different points of view that we're going to talk about in a minute. Here I'm going to remind you what derivatives do. And again, I know everybody's sort of reflexive memory from high school is that derivatives are slopes on graphs. I'm sure y'all are. I'm trying to build up reflexes and mental reflexes in y'all that whenever you hear the term derivative as a slope, you know, on a graph, right? Specifically. So I want to take a different point of view here. I want to view derivatives now in this context as being relationships between velocities. So if you have an input velocity, x prime, then the derivative is what you multiply that by to get the output velocity, y prime. So again, there's different ways to think about this. You can view this as what should be a primary interpretation of derivative, single variable derivative, right? Input changes to output changes, after all, right? And if you think about it, you can also view this itself as being kind of a use of kind of an instance of the chain rule in a way, right? Because dy dx, let's see here, x prime could be written as dx dt, and then the product gives you dy dt. How about that, right? So it's sort of a different point of view, whatever. I want to view this as being a primary fundamental interpretation of a derivative. Okay, so with that in mind, let me now compose a couple of functions here. So, we have f turns x's into y's. Then we have g, that turns y's into z's. I'm taking the y outputs from the f, making those the y inputs into the g, altogether then giving me a composition. See, how am I going to draw this? Composition kind of like this, that takes x as the input and gives z as the output. All right, so we've got two functions and their compositions. Everybody on board so far? And you can write down what the derivative does in each of these cases, and I've written those down here. That's what a derivative does, that's what a derivative does, that's what a derivative does, and you can take those and kind of plug the one into the other and write down the algebra, blah, blah, blah. The way I'd prefer to think of this is that if you are keeping track of how fast are these variables changing, the action of applying the function f multiplies this velocity to get that velocity, specifically by multiplying by a factor. That's what derivatives are. They're multiplicative factors. You can see right here, dy dx is the thing that you multiply by x prime to get y prime. So the chain rule, my sort of hand-waving case that I'm going to make here for why the chain rule should be intuitively satisfying is that if you multiply by one factor and then subsequently you multiply by another factor, so you multiply by one factor, then you multiply by another factor, all together you have multiplied by the product of those two factors. Right? And because that's how multiplication works, right? You multiply by 3, and then after that you multiply by 4. Altogether you've multiplied by 3 times 4. Right? Pretty believable. So that's, again, a point of view on what's going on here. That gives you your familiar Leibniz form of the single variable chain rule. There you go, that you all remember. By the way, notice a nice point of view on this is that differentiation turns compositions into products. Right? If you're composing functions, then the derivative of the composition of those two functions is the product of the individual derivatives. Okay. All right. This is all single variable calculus. A different take, perhaps, on something that I know that y'all already know. The reason I gave you that is because now I'm going to make morally identical argument in a multivariable context. Not the same, it's a little different, it's multivariable, the pictures are going to look a little different, but it's morally the same case. So what do derivatives do in multivariable calculus? Well, again, they're factors. The derivative is what you multiply by input velocity to get output velocity. Just like in single variable. I mean, it's a matrix that you're multiplying by a vector to get a vector instead of a scalar that you're multiplying by a scalar to get a scalar, right? So sure, it's a slightly more, it's a different details, but it's a factor you multiply by input velocity to get output velocity. You can then, again, you can compose. You have two multivariable functions. See, I here have f, that's a multivariable vector valued function. I'm composing that with g, multivariable vector valued function. And again, you can write down all the statements about, for each one of these, how the derivative is a factor, a matrix factor. But just like in single variable, again, you can write down, you can plug the one into the other and compare and the blah, blah. But really what it comes down to is that when you multiply by one factor and then subsequently you multiply by another factor, all together in the composition, what have you done? Well, you multiplied by one factor, then you multiplied by another factor. That's morally the same as multiplying by the product of those two factors. And so again, you get a now different notation, sure, right? But the derivative of a composition is a product of the individual derivatives, just like in single variable. They're matrices now instead of scalars. That's the only difference. Everybody buy it? Does it seem kind of reasonable? Okay. All right. Now, in this picture that we're looking at, I drew the picture here for functions that have, let's see here, I had 2 dimensions, and then 2 dimensions, and then 2 dimensions. How does that change if, let's say in the y space, let's suppose that was 3-dimensional. How does that change the argument? And the answer, as I see it, is it changes the argument by requiring that I draw a little third axis there, and other than that, it doesn't make a bit of difference at all. Right? It's still the case that the derivative of f is the matrix that turns that vector into that vector. If that vector is 3-dimensional, so be it. Whatever. Who cares? Right? Likewise for the dimensions of any of these other spaces. So I drew the picture for sort of, entirely 2-dimensional, but there's no need for that. This works for any dimensions. Okay. All right. Let's get an example. Done. A couple of functions, f and g. Notice the way I have this set up. It's just like in the picture on the previous page. Whoopsie. Let's see here. On the previous page, let's see the first function, f, took x's as the inputs, gave y's as the outputs. The second function, g, takes those outputs from f, the y's, and it makes those inputs, and then out come the new outputs, the z's. And notice what the question is asking. The question is asking to compute the derivative of the composition, and furthermore asks for a specific partial derivative. Now notice this is a partial derivative of, this is going to be hard, partial derivative of z3 with respect to x1. Right, so that's one of the eventual output variables, partial with respect to one of the original input variables. Everybody with me? All right, so we'll deal with the second part of the question in a minute. First thing I want to do is, if I can do that, there we go. Let's focus on finding the derivative matrix. Here we go from the previous page. Right, we want to take the derivative of the composition. It's the product of the derivatives. Notice in the statement of the question, I didn't actually give you all formulas for these functions. There is no formula for f. There is no formula for g. How are you going to find the derivative matrices? I saved you the trouble. I gave you the derivative matrices. Right? Now, you do have to be careful about a couple of things. First, are these derivative matrices evaluated where they're supposed to be? That matters. Got to be careful about that. Apparently, I want to know the derivative of the composition at the point 1, 2. That means that df needs to be evaluated at the point 1, 2. Oh, cool, it is. Sweet. I was given the exact df matrix that I needed. Okay, here, let's see. Because I'm evaluating the composition at 1, 2, I am also going to need to know, it says right here, the derivative of g at f of 1, 2. Was I given dg evaluated at f of 1, 2? Well, let's see here. I was given it evaluated at 3, 1, 0. I need to know what I need it evaluated at f of 1, 2. it's not immediately clear that that's what 310 is until you look over here and notice, yeah, that was given also. F12 is 310. So you need that information as well to make that work. Is everybody with me? Okay. All right. Another thing we need to worry about is the order that I write these matrices down in. The order is very important, as you all recall from linear algebra. Matrix multiplication is not commutative. You can't switch the order of the matrices. It's not okay. It just doesn't work. Right? So which order is it? Good news, the order that you write them down in the composition is the same as the order that you write them down in the product. That's nice. Right? So easy little memory trick there. Handy. Here's the bad news. If you go back to the diagram, let's see, let me clean up my mess here. Go back to the diagram. This is the diagram for the chain rule as I've written it down here. Notice that the first function to act is f, which is on the left because it's a diagram. We write diagrams left to right. Right? That's just, I don't know, there's no particular reason, but that's just the way it is. Right? And yet f is the function for the derivative matrix on the right. And that's very frustrating, right? Heads up. There's nothing we can do about this, right? Ultimately, this traces back. If you really trace, who's the guilty party in making this unfortunate coincidence come about, right? This little tragedy. It comes from the way we write functions in the first place. We have a point A. There it is. There's A. Now I'm going to apply f to it. Notice in the diagram, f is to the right of the point A that I'm plugging into it. Of course it is. I'm going left to right. And you enter the algebra, we write the function on the left. We always have since, I don't know, when did y'all first see functions? Like middle school or something? I don't know. So why do they write the function on the left when in the diagram it's clear on the right? And it causes nonsense like this to happen. And this is dangerous, and you can get burned bad by having accidentally putting these functions in the wrong order. I know because I made that mistake one time when I was in graduate school. And in graduate school, you don't do homework sets particularly, where you work on a question. A hard problem takes you, an hour, right? In a graduate program, a hard problem takes you months, right? So I made not exactly this mistake, but something that's morally equivalent to this mistake, and didn't discover my mistake for about a month. And then when I made that discovery, I had to admit, okay, well that means that every calculation that I've done since then is all trash. It's all wrong, and I had to take a month's worth of hard work and throw it in the trash can. So I don't make this mistake anymore, right? I am constantly scared to death that I'm going to accidentally make this mistake, and I'm always extremely careful to think it through. Wait a second, which way does it go? Which function acts first? In which one's on the left and on the right? And depending on whether you're looking at a diagram or a composition or a product, right? You have to be very, very careful and always worry about that kind of thing. So I tell you that story so that hopefully y'all don't have to, learn from the school of hard knocks, right? Like I did in that case. And hopefully y'all will just remember from my story. Always be careful to think about the order of the functions. Is that cool? Okay. All right. Yeah. Okay. Okay, so back to this example. We've got the right matrices, just happen to be given. That was nice. I multiply them. I'm very thoughtful here to multiply them in the correct order. First function first, second function second, keeping in mind that when you multiply matrices, the one on the right is the one that acts first. just as in compositions, the one on the right acts first. And then likewise, matrix multiplication, the one that's on the left acts second, just like in compositions. But the opposite of both of these are the opposite of what it looks like in the diagram. Okay, so then you take the matrix. Oh, and by the way, look what I did here. By the way, I did the following on purpose, right? Just to catch. Let's see who's paying attention, right? I gave you the F matrix on the left in the statement of the question, right? And then you have to think to put it on the right, and vice versa. I gave you the DG matrix on the right, and you have to think to put it on the left. I am not above that. Right? So, and again, this is an important idea. This is how I test the important idea of who is appropriately careful and thoughtful about this very important matter of which way do the matrices go. Does that make sense? Okay, so don't get stung on that. Yeah, okay. All right. Okay, and then you multiply the matrices, and here's your answer. And so we now have if I can tap the thing, there we go. The DG matrix that we wanted to compute is this right here. Okay, second part of the question. Second part of the question is to find this specific partial derivative. Partial of Z3 with respect to X1. We have the matrix that consists of all of the partial derivatives of the composition. This is one of the partial derivatives of the composition. It's a partial of one of the eventual outputs with respect to one of the original inputs, right? So it's somewhere in this matrix that we just computed. Which one is it? Okay, well, the way you keep that straight is you note that Z3 here, the thing whose partial I'm interested in, that is the third output variable right there in the list. Being as it is the third output variable, we are looking in the third row of that matrix. Remember, output variables correspond to rows. Is that cool? Everybody remember that? Yeah. Okay. Now, which one is it? Well, we are looking for the partial with respect to X1. That is, you'll notice, again, in the given, the first original input variable. And that means that we're going to look in the first column. So specifically then, the partial derivative that I want is that element. And it's 3. Everybody happy? All right, a lot of little detail devils in there that have to be talked through, and there we go. Okay, a couple of quick special cases that I want to talk about. These are just special cases. There's not a tremendous amount that needs to be said here. I'm going to basically wave my hands at the examples that we have here. But here I have a composition, and notice in that composition there is one sort of nice little convenience. Notice there is only one original input variable. And so I just like to point out how that makes the chain rule look. In this special case where you have exactly one original input variable, you might see this coming. Being as there's only one variable, I'm going to view it as being t, because then I have everything as a function of t, and that means that I can view these functions, some of these functions anyway, as parametric curves. So specifically, let's see here, this function right there, position is a function of time. That's a parametric curve. And I can write down its derivative matrix, and it's the derivative of that parametric curve. Well, of course it is. Let's look now at the composition. The composition, position is a function of time. Now it's just position of the composition in Rm as a function of time, right? But still, its position in now a different vector space is a function of time. So its derivative matrix is also just the derivative of a parametric curve. Right, so what we conclude from this is that in this weird special case where there's exactly one original input variable, this function here, the sort of right side function, right? You can think of the right side function as being sort of, this is really the function that we're actually looking at. F is the function whose derivative matrix, df, we're trying to understand. And it's as if I have a parametric curve in the domain that I plug into f, producing a parametric curve in the target, and the derivative matrix, df, just relates input velocities and output velocities. This is old news. We already knew this. Right? So I think it's kind of nice that the chain rule, in this special case where you have a single original input variable, everything's a function of t. You can think of the chain rule again as just as giving an interpretation, reproducing an interpretation of derivative matrices. They relate input velocities and output velocities. That's it. I think that's cool. So this example down here is just exactly that. I have a function here. This is the function for which there is a given input velocity, and the question is to compute an output velocity. That's what derivative matrices do per the formula on the previous page. So the relationship between this input velocity, oh gosh, I'm not good with my left hand. Relationship between this input velocity and that output velocity is the derivative matrix. That is the thing that you multiply by the given input velocity to compute the requested output velocity. And the result is just a matter of the arithmetic. Everybody on board? All right. Here's I'm going to say another special case. I don't know. It's morally kind of the same thing. Again, notice in this special case we're going to entertain here, we have, again, just the one original input variable. Everything's a function of what I'm, of course, as I often do, everything's a function of what I'm going to choose to call t. Position is a function of time. The additional special case here is that we also have only one eventual output variable. And that means that the composition, well, it means two things. The composition, though, is from R1 to R1. That means that in the chain rule, I'm computing a Calc 1 single variable derivative. Like just straight up, one variable in, one variable out, just the derivative. Right? And notice now in this special case, you can think through what else is a consequence of these assumptions that we're making here. We have one eventual output variable. That means there's only one row in the left matrix, and we only have one original input variable. That means we only have one column in the right matrix. Notice again the little sort of apparent switcheroo between the order in which these functions appear in the diagram and the order that their derivative matrices appear in the chain rule. Again, don't step on that landmine. Right? School of Hard Knocks and all that. That's how the chain rule breaks down in this case. Now, something else kind of cool happens here, and that is that you can look at this left derivative matrix and notice that this matrix vector product, as I have it written here, is morally a dot product, right? I mean, if I take this row matrix and just kind of turn it on its side, right, and kind of treat it like it's a vector, which again, the multiplication, it would be the same as doing a dot product. What that turns into then is the gradient of the function, the right function, right? That's being dotted with the velocity of the first function. Everybody good? So, I mean, it's kind of a similar sort of a punchline. Dot product with the gradient, when appropriate, when it's real valued. You can only talk about a gradient when it's real valued, right? But dot product with the gradient relates input velocities with output velocities. I guess you could kind of view this as being a velocity of sorts, right? Dot product with the gradient does the same thing as multiplication by the derivative matrix. Okay. All right, and again, example, input velocity, output velocity, dot product with the gradient to do it. So I'm going to let y'all read this example. By the way, I need to keep a more careful look on the time. I have 2.25 minutes left. Okay. So I want to talk just a little bit about intermediate variables. We're going to build up to a different point of view on the chain rule. Now, I very deliberately started us off with what you might call a matrix point of view on the chain rule here, right? So we've got the chain rule says that the composition derivative matrix is a product of the individual derivative matrices. All about matrices. Ultimately, this is the most natural way to think about it. Look how simple it is on the page. Derivative of composition is the product of the derivatives. It even rolls off the tongue the same as single variable chain rule does. So I did that on purpose. I think that should be everyone's sort of cornerstone, default, fundamental point of view on the chain rule. That said, in practice, sometimes it's nicer to have a coordinate point of view on the chain rule. Don't think of the objects in question as being vectors. Sometimes you just want to look at one coordinate at a time, that kind of thing. So here we go. Here's our matrix chain rule. Right? Derivative of a composition is the product of the derivatives. Notice that the variables line up accordingly, right? F turns x's into y's. Thus, this derivative matrix, partials of y's with respect to x's. G turns y's into z's. Thus, this matrix. The composition turns x's eventually into z's. And thus, these are the elements in this product derivative matrix. And all we're going to do here is just look at one particular element of this product matrix. How would I compute that one particular element? And the big idea is you just notice that, that element is in one of these rows. That tells you which row of the left matrix is going to be involved in the dot product computation. And that element of the product is also in one of the columns. That tells us which column of the right matrix is going to be involved. And then I literally just do a dot product. Right? So altogether then, this is the formula that you get. The formula for that one particular element of the composition derivative is computed as a dot product, which you can see are all the various elements of that green row multiplied by all of the various elements of that blue column and added together as dot products do. Everybody good? All right. So there's a bunch more to say about this. We'll pick up with this next time. I can infer from that we're out of time, so we'll call it a day. See y'all next, let's see, when would it be? Monday, I guess it is. Y'all have a great weekend.